Welcome, everyone. I'm Liz Sykes. I'm the president of the Geochemical Society, and I want to thank you for joining us on this special occasion, the special presentation of the Geochemistry Fellows. Today we are recognizing a large and diverse group of scientists who have made major contributions to our field. Their distinguished careers are marked by excellence in research, outstanding teaching, mentoring, and community service. The EAG and the GS are proud to celebrate their achievements with this distinction. We would like to express our gratitude to the members of the Fellows Award Committee for their hard work evaluating 65 nominations. Theirs is a difficult task of choosing 14 new fellows out of so many outstanding nominees. We are also grateful to the members of the award nominations committees for their remarkable work soliciting nominations, and we wish to thank everyone in the community who took the time and efforts to submit a nomination. If you know a member of our committee deserving of this recognition, we strongly encourage you to nominate them for next year's class of fellows. Both societies wish to recognize a diverse international group, and we cannot do that without good nominations. So look left, look right, and think of who is deserving. In addition to our new 2025 fellows, we are also honoring some fellows from 2024 who could not receive their awards last year. I will ask Dan Frost, president of the European Association of Geochemistry, to begin the introduction of our new fellows. Dan.
Thank you, Liz. So we're going to start, as Liz said, with the fellows from 2024 who couldn't be at the meeting last year. So Dereya Ayalu has made important contributions to the study of magmatism in the East African Rift and the flood basalt systems of Ethiopia. His insights and collaborations have helped usher in a new era in the understanding of the magmatic processes in this critical region. Okay, thanks. Joachim Brox is recognized for his research. Oh, sorry. Joachim Brox is recognized for his research on the molecular evidence in sedimentary records that attest to the timing of the evolution of eukaryotic organisms on Earth. His work has had a profound impact on the understanding of the progression of life on Earth, redefining the principles that serve as validation of molecular evidence for ancient organisms. Christine Putnis is an influential scientist who is one of the pioneers in discovering the process of coupled dissolution and precipitation at mineral-water interfaces, a concept that was misinterpreted by many geochemists for decades. She's also been especially active in raising research funding for entire communities of scientists, advising researchers, and generally serving the geoscience community. Urs Schaltiger is the global leader in ID.TIM's uranium-lead zircon geochronology. He's made seminal contributions on the timing and tempo of magmatism in the crust, answering fundamental questions such as the timescales required for both pluton assembly using zircon petrochronology and the formation of large igneous provinces. He's also led community initiatives to continuously redefine uranium-lead isotope geochronology. His significant editorial and administrative roles while all the time generously supporting others. Helen Williams has discovered that iron isotopes become fractionated during mantle melting and redox processes. This was an unexpected result, and she has successfully applied this and other heavy stable isotope systems to understand processes, including the origin of the Earth's core and melting beneath mid-ocean ridges, ocean islands, and subduction zones. In addition, Helen has served on the EAG Council and several committees for the EAG and Geochemical Society. She co-chaired the 2019 Barcelona Goldschmidt Conference, and she is an editor for Geochemical Perspectives Letters and Geochemical Perspectives. And now on to the fellows from 2025. Michael Bowell's scientific contributions laid the foundation for the numerous applications of trace element geochemistry and have addressed biogeochemical questions related to both the modern world and early Earth. He has contributed a fundamental understanding of rare earth element geochemistry, which he expanded to include yttrium. His studies on a wide range of geological, hydrological, and biological materials helped establish the fields of environmental geochemistry of critical metals. Professor Bao has served as a counselor and board member of the EAG and the DMG. Ian Campbell's pioneering research has revolutionized geochemistry, clarifying the role of mantle plumes in large igneous provinces, surface volcanism, and extinctions. His work in ore deposit geochemistry, magma chamber dynamics, and isotopic methods has profoundly advanced our understanding of resource formation and continental crust evolution. Alain de Vol is recognized for his outstanding contributions in marine biogeochemistry, especially elemental cycling in low oxygen water and sediment environments, for his generosity and leadership in mentoring and training the next generation of geochemists, and for his commitment to excellence and equity in building community science infrastructure. Unfortunately, Alan couldn't be here today, and we hope to recognize him next year. Timothy Eglinton is recognized for his achievements in compound-specific radiocarbon analysis and other areas which have transformed the field of organic geochemistry and have had a profound impact on various science disciplines. Ellen Hopmans has made significant contributions to organic geochemistry, particularly through pioneering analytical advances. She introduced liquid chromatography, enabling the detection of membrane-spanning lipids like GDGTs, revolutionizing paleoclimate research with the TEX86 proxy. Additionally, her teaching and mentoring have inspired and empowered the next generation of organic geochemists, especially women. Dmitry Ironov is recognized for his contributions to our understanding of the compositional variability of Earth's interior and the processes that determine that variability, along with his expertise in collecting and identifying samples best suited to additional studies and his willingness to provide these samples openly to the broad geochemical and geophysical community. Baltz Kamba has made paradigm-shifting contributions across multiple fields of geochemistry. These include the nature and evolution of Earth's earliest lithosphere, the use of rare earth element contents in microbial carbonates as paleo-redox proxies, employing mineral aerosols to track dust provenance, and key aspects of fundamental geochemical cycles. His research, while academic in nature, often has a strong societal component involving interactions with policymakers. Hodaka Kawahata is a chemical and paleoceanographer who conducts experimental research in both the laboratory and the field. He served as president of the Japan Geosciences Union and the Geochemical Society of Japan, and has been a strong advocate for both diversity and for the support of early career researchers, having also supervised more than 20 PhD students himself. Carsten Munker developed and improved analytical methods for high precision measurements of isotope ratios and element abundances. These led to innovative and groundbreaking studies on the history of the solar system and the evolution of a differentiated Earth. Thank you very much. Martin Reich is renowned for advancing the understanding of planetary scale processes that control the formation of mineral resources, elemental and isotopic cycles, and their link to global climate change. His work spans macro-scale geological processes to atomic and nanoscale fluid-mineral interactions, offering profound insights into ore-forming mechanisms. His commitment to fostering international collaboration has given students valuable exposure to South America's geological diversity. Sarah Russell is a leader in cosmochemistry and planetary sciences through her detailed insights of meteorites and sample return mission materials. She is a generous colleague to many scientists and devotes considerable time as a journal editor and workshop organizer. She is a highly effective science communicator and role model, particularly to the large number of PhD students that she has helped to graduation. Maria Schönbeckler is a pioneer in the modern era of isotope geochemistry. Her development and application of the analytical techniques needed to resolve isotope variability in meteorites caused by nucleosynthetic variability, short-lived radionuclides, and cosmic rays have dramatically advanced our understanding of the processes operating in the early solar system. Avner Vengosh is recognized for his work evaluating the impact of conventional and non-conventional energy development on environmental geochemistry, especially of water resources. His work has influenced both science and public policy in areas such as the water quality effects of hydraulic fracturing of shale gas production and coal combustion residuals. Christina Yan Wang has made major contributions on the igneous petrology and geochemistry of mafic ultramafic rocks and the economic geology of magmatic nickel-copper PGE sulfide deposits and iron-titanium oxide deposits. She has consistently demonstrated her dedication to the international geochemical community through her exceptional editorial contributions to academic journals and her invaluable mentorship of the next generation. Marjorie Wilson's research has led to fundamental insights into the petrological evolution of continental and oceanic magmas and their dynamics. Her influential work is highly regarded throughout the magmatic community. She has been the executive director of the Journal of Petrology since 1994. Finally, we'd like to also acknowledge Sarah Jane Barnes, who could not be here today. We hope to recognize her next year in Montreal. Let's give all our new fellows one more big round of applause. So, thanks a lot for your attention. I now invite Karen Hudson-Edwards to introduce today's plenary lecturer.
Hello, everyone. Welcome to today's plenary talk. As Dan said, I'm Karen Hudson-Edwards, one of the co-chairs of this year's Goldschmidt meeting. I have the honor of introducing our plenary speaker for today, Fantong Wilson Yeto. So Wilson did his BSc at the University of Buea in Cameroon, his MSc in Applied Geology with a hydrology option at the same university, and his PhD in hydrogeochemistry at the University of Toyama in Japan. He's currently a Chief Research Officer at the Institute of Geological and Mining Research in Cameroon, where he was named Best Junior Researcher in 2011 and then Best Senior Researcher in 2018. He holds several other eminent positions, including Chair of the Scientific and Technical Committee of the Global Water Partnership Cameroon, and a Chief of Service in the Scientific Policy and Planning Division of the Cameroon Ministry of Scientific Research and Innovation. At the Institute of Geological and Mining Research, Wilson leads the Hydrology and Climate Change Unit, where his research focuses on hydrosphere, lithosphere, Earth factories, which I think is an amazing term to use. I've never heard it before. He's published widely on environmental topics such as water quality, water quantity, environmental health, natural disasters, and mitigation of carbon dioxide explosions from lakes. Today, he's going to speak to us about fluorosis and the hidden smiles of the Sahel. Please join me in welcoming Fantong Wilson Yato to the stage.
Good morning to everybody. I want to thank all of you for coming here this morning to listen to the talk that you find on the slide. And I want to be specifically thankful to the organizers of this Goldsmith Come Together, which has a peculiar characteristics of a more inclusive Goldsmith 2025, which I believe has paved the way for me to stand here today. We shall be conversing this morning on the topic that you find on the board, fluorosis and the hidden smiles of the Sahel, a geochemical tale. Before I go into the flagship content of the discussion I want to share with you this morning, I want to give you two small milestone stories of how all of this happened. When I grew up like a child, my father got to realize that I didn't like to go anywhere where there is water. And at one point, he decided to take me on holiday to the coastal city called Douala in Cameroon, and arranged that we're going to get into a ship. So by the time we got to the dock, I told my father, in as much as that ship is floating in water, I'm not entering into it. And he was very furious, and we left. As a freshman in the university, I thought of what I'm going to do not to get into water. I said, okay, I'm going to do rocks, seeing rocks are hard, naively. So I registered to do geology. I got a BSc and MSc in geology, got recruited to the Institute of Geological and Mining Research, and my first assignment was to do gold exploration in the eastern part of Cameroon. And when I reached there, I saw about 3 infants with their parents and their grandparents doing artisanal mining. And at one point, these children were crying out of thirst. They wanted to drink water. And I saw them actually getting water from one of the mining pits, water that was really dirty and polluted. And as they were about to drink this water, I had my mineral water with me. I stopped them and I gave them my mineral water to drink. And at that point, my perception of water changed. By the time we got back to base, some American universities, like University of Michigan, called me up to do igneous petrology, and I turned it down. And I continued to search for scholarship to do hydrology or hydrogeology in order to be more, useful to children and people who don't have access to water. So the irony of all of this is that there is a say in my dialect that the things that you don't like come your way, and the things you like go away. And that is what happened to me. And now I stand here to speak as a hydrogeochemist, whereas I didn't like water at the beginning. The second small story I want to share is that when I got my scholarship to do hydrogeology in the University of Toyama in Japan, I went out on the field in March 2007. That was the peak of the dry season. And I collected close to 300 water samples from wells, boreholes, springs, rivers. And when I got to the lab and did the analysis, my objective was not to look for fluoride. I was out there to characterize water chemistry and water quality for various uses. But the initial data that we generated in the lab showed that there were a lot of undesirable fluoride concentration in the samples that I collected. And my supervisor at the time pulled out an atlas of IGRAC 2006, that is the International Groundwater Association Center, and told me, look at this map. There is nothing that indicates in this map that Cameroon has a problem with fluoride. So you can't tell me that 40% of the samples you collected are rich in fluoride. He was a bit nervous and asked me to tell him where my remaining samples were. And I produced, this was the very first map that I'd ever produced using ArcView version 3.2 with all the excitement to show him where the fluoride hot spots were. So I folded my map, put it in my pocket, and went back to my desk. 3 weeks after, he called for me and said, Wilson, I'm sorry, you were correct. But what is the evidence that this fluoride is affecting the population? I had to get back to people in Cameroon, and we got some guys who told me, the medical doctor who is in charge of public health in your study area is your classmate, so you can talk to him. So I called him, and he told me, what am I talking about? I explained the symptoms to him, and he said, wow, so this is what I see here every day, but I don't know where it's coming from. And I thought that since we're in the northern region of Cameroon where you have a lot of Muslims, and they eat a lot of kola nuts, maybe their children too are eating kola nuts and their teeth are getting bad. And my supervisor said, okay, that be the case, you have to publish your first paper so that we can apply for a grant for you to get back to the field the second time, which we did rapidly, got the first publication, and I applied for the Sasakawa Foundation in Japan, got the grant, and went back to the field. And I went back to the field. I co-opted medical doctors and dentists with whom we worked on the field together. As we can see in this picture, for every 10 children that we found in that area, 6 or 7 were identified to suffer from dental fluorosis. And whenever I went out on the field, today I am here in Prague. We are having a very good time in a very good Holiday Inn hotel. And the path to sleep in the Holiday Inn hotel starts in this hotel here on the field. This is where I spend most of my time on the field to generate the data, that we're going to talk about now. Thank you for listening to that story, because the environment here is quite harsh. I took this picture at the beginning of the rainy season. That's why you see some of the leaves are green. Otherwise, this is always very dry. The temperatures go as high as 50 degrees Celsius sometimes. You sleep and they call you that, hey, the neighbor in this next hut has died due to heat waves. But you need to be there to make sure that you generate the data in order to contribute to science. After all of this, 2 years after, the updated version of the distribution of fluoride in groundwater was published by IGRAC, and the map that my supervisor showed me, without Cameroon being on this kind of a map, has changed. And now Cameroon had an indicator of what? Of medium concentration of fluoride in its groundwater. To put all of this within the context of a scientific problem, we all know that the 9 planetary boundaries, which are climate change, biosphere integrity, land system change, freshwater change, hydrogeochemical flow, ocean acidification, atmospheric aerosols loading, stratospheric depletion, ozone depletion, and novel entities. Out of these 9, 6 of them have transgressed the safe boundary. And within these 6, the freshwater change and climate change nexus is what we are distilling in this story this morning. In the study area, we have surface water flowing just for 3 months in a year. So you find river channels really dry. All the time you just see a sea of sand. And in the evenings, if you pass by, you might feel that there is a football match that is going on, because Cameroonians really like playing football. Whereas, what they are doing there, they are digging into the sand to get water for various uses. And because surface water is, not readily available for various uses, there is a high demand for groundwater. And this groundwater is really rich in this fluoride we're talking about. And when they consume this fluoride, this is what happens to the children. And as I said before, the cause of this problem was not known before we did this work in 2007. And the other, tricky corner of this is that all the families who had children that were suffering from dental fluorosis were stigmatized for practicing witchcraft. And the children never felt free to socialize. They were not inclusive in many activities. They were always secluded in the society. And at one point, when we started this work, we thought that geochemistry or hydrogeochemistry is going to come in as a bridge, to clarify all of this, or to fight for these children so that they will become socially inclusive. The location of the hotspot of this phenomenon, as we see in the map, We have the Sahel of Africa, and we have the East African Rift. And coming down to Cameroon, we have 5 major hydrological basins in Cameroon, which are the Lake Chad, the Niger, the Senegal, the Congo, and the coastal, as you see on that map there. And out of these 5, 2 of those hydrological basins, the Chad hydrological basin and the Niger hydrological basins, are the basins which have anomalous concentrations of fluoride in the groundwater. In this area, we can see from there that the atmospheric temperature in the northern part of that country is about 28 degrees, although sometimes it goes up to about 50 degrees Celsius. And rainfall depths are really low and reducing in the context of climate change, while evaporation is very high. And with this high atmospheric temperature, it is causing the availability of surface water resources to get more and more limited. And as we said earlier, the demand for groundwater gets really high. And because most of the local people in the communities have gotten to know that there were people working already on this fluoride issue, whenever we get out on the field to do analysis or to do sampling of groundwater for chemical analysis, the whole population come out like, you feel like they're telling you, we're going to join you in this fight to kick this fluoride out of our water. They don't even give you the space to collect samples. So there are 2 concerned with what is happening and looking forward for a fast solution. And as we listen to this talk, I want us to pay more attention to the attention that we give to the society and not the science at this point in time. So these are the manifestations in some of the villages in that area for fluorosis. And in the hydrological basin further south, in the Niger River basin, you have some of these corridors of hotspots of fluoride concentration, and with the same effect on school children mostly. In the southeastern portion of the Lake Chad basin, we've also found out that there are a lot of hotspots of high fluoride concentration. So the entire sub-region is like having fluoride in groundwater that people use for most activities. We all know that the cause of dental fluorosis is due to a concentration of fluoride as high as ranging between 1.5 and 4 milligrams per liter in drinking water. Looking at this value that was prescribed by the WHO, we thought that we should contextualize the norms of fluoride, because the 1.5 milligrams per liter threshold that was given was determined by Gallagher and Vermeulen in 1957. And one of the parameters that they used in their equation was the atmospheric temperature, which they considered as 16 degrees Celsius, which is going to enable the consumption of 1 liter of water per day per person. But in the study areas I've told you earlier, the atmospheric temperature goes up as high as 30 degrees Celsius. That's about twice the value that was considered in the equation to determine the threshold of fluoride in water. And personally, when I go out on the field in this part of the country, in a day, I consume 6 bottles of 1.5 liters of water. That's about 9 liters of water per day. So it made us to understand that the assumption that we consume 1 liter of water per day per person, and considering 16 degrees Celsius, to prescribe 1.5 milligrams per liter of fluoride in drinking water, we thought that it was a bit, out of place in our local context. So we substituted in that equation of Gallagher and Vermeulen the atmospheric temperature that we have on the ground. And we realized that the upper limit of fluoride in drinking water in that area should be 0.75 milligrams per liter. So that gives a climate change angle of this work, which we're going to be exploring later on. So after realizing all of this, we went into a consultation with the local people, all the stakeholders, involving university lecturers, university students, and NGOs, indigenous communities, for them to get involved in the problem identification. And when we did this, we all came out with some outcomes and some resolutions. And we're told that we should actually recheck the groundwater chemistry to confirm the fluoride content in the water. And if the concentration is confirmed, then we should do some capacity building on the fluorosis-defluoridation nexus and propose solutions. Now, to get all of this done, we needed funds. Some organization paved the way for me to give talks, during parliamentary sessions, so that the parliamentarians can mobilize some money, especially parliamentarians from this area. I did, a litany of presentations. And then, at the local level, to traditional authorities. But all of that fell in deaf ears until one day, UNICEF Cameroon called me up and gave some seed funding in 2017. And in 2021, we got the second seed funding from the Swiss Development Corporation, which has been enabling us, to generate the data that we have in this study. So, we went out there, and I selected this area because when we did this work in 2007, the sample point, you could see those grids there. I made sure that I got samples from each of those grids, and the samples from each of those grids were not representative, so I selected this area which had the highest concentration of fluoride of about 15 milligrams per liter, and we zoom in there to get this area which has about 36 villages. So we did a more detailed work in that area, did some training, some beginning citizen science to make sure that everybody around that area, students, local guides, and all of that, on how to do sampling so that they have an idea of what is happening. And we got the samples sent to the lab. There is a national lab at the Institute of Research for Geology and Mining, which did the measure ions and the trace elements and heavy metals were done in Hanover, Germany. And the results that we got showed that, of all the 36 samples that were collected from each of the village, only 4, contained desirable amounts of fluoride below the local norms that we calculated, 0.75 milligrams per liter. What is the provenance of this fluoride? We have this granite on the field, and in this granite, from where we collected samples, we realized that there were secondary minerals that were formed in the veins, in secondary veins in this granite. And when we did the thin sections, we picked up the secondary mineral fluor-apatite in the granite. And as we all know, with water-rock interaction, the fluorine in these minerals get dissolved into the water bodies to increase the concentration of fluoride in groundwater. And there were some geochemical processes that mobilizes the fluoride in the water. Some of them include the presence of sodium. We realize that the increase in sodium, favors the free mobilization of fluoride in water because sodium has a very zero affinity for fluoride, unlike calcium. When the pH gets higher, it also mobilizes fluoride. And again, the older groundwater, based on tritium age data that we got, the relatively older groundwater contain more fluoride than the younger ones. And again, there were seasonal variations. In the rainy season, the fluoride concentration got lower, and in the dry season, the fluoride concentration got higher. So we started looking for various options to solve these problems. And the options to solve these problems, we had 3 of them. The first possible one is to use the alternative source of water for drinking, which could be surface or rainwater. The second is to change the eating habit, by consuming food that is rich in calcium. And the third was to defluoridate the groundwater sources that are rich in fluoride. So looking at each of these, the first alternative was not feasible because, as we've seen earlier on, we realized that we don't have surface flows. The rainwater depths are very low, so it would be needless to rely on either surface flows or rainwater as drinking water sources. As for diet that are rich in calcium, this is an area where the people, level of income is really low. They eat what they see, so we didn't have to condition them to buy food that is rich in calcium. So that, again, was excluded. And we thought that the best option to solve this problem was to do total defluoridation because in this part of the country, you have a lot of herders. They have huge number of cattle that are being killed every day, and the bones are littering in the environment and dirtying the environment, and we thought that these bones are rich in calcium, so we could get this calcium from the bones, and because fluoride has a high affinity for calcium, we can use it as a filtration material. And secondly, in the nearby area, there is a rich exposure of marble, which is also rich in calcium. So we thought that with the availability of these materials, which are cheap and readily available, we could transform them to get prototypes of defluoridation filters to see how far we're going to solve this problem. So we opted for the defluoridation process. And to begin this defluoridation process, we had to construct a pyrolyzer using local materials. We constructed a pyrolyzer which we use, as a furnace to pyrolyze the cow bones to a maximum temperature of about 600 degrees Celsius. Sometimes the temperature has to, come down to about 450 for us to actually get, the bones calcinized in a way that they will have a high, ability to get the fluoride out of water. So we constructed the pyrolyzer and then collected raw bones from the environment. You can see in the back there. So we get the young boys around. They were quite busy. We kept them working. They collect bones from all the slaughterhouses. They wash them overnight. You could see them getting cleaner there, removing all the spongy areas, and we're targeting only the femur and the hard parts. And we now do the pyrolysis in the furnace. And when the pyrolysis is done, we realize that some of them were quite good when they get darker, but this one was not really good because it's a bit gray in color for various reasons, which I will explain later. When we got these pyrolyzed bones, we got them pulverized in an agate mortar. We sieve them, we wash them, we dry them. We wash them to render them clean because we know from our elementary schools that drinking water should not have color, it should not have odor. So we try to put this filtration material clean so that the water should at least have the characteristics of a drinking water at the end of the day. We also went down to the field where we have a wide exposure of marble, and we got some marble samples, and we produced grains, and came back and used the grains of the pulverized bone chars and that of marble that we produce, to come out with prototype filter materials, defluoridation filtering materials, with various grams of the cow bones char that we produce, various quantity of the marble that we got. So we had altogether about 6 prototypes, and one of them, we decided to maintain a commercial filter the way it is that we bought it in the market, because when we got this, we now fit in, we adapted these filters accordingly, but filter G, we didn't adapt it. We left it the way we bought it. And we dispense about 15 liters of water through them, using a time span of between 7 to 14 hours. And at the beginning, this is what we got. You see, the water was quite dirty, but we kept on adding more water in the filtration system until the water got clearer after using a very huge volume of water. So when it got clearer, with no smell, we now do the analysis. And when we did the analysis, we realized that the filtered water was dominantly calcium magnesium nitrate, while the unfiltered water was calcium magnesium bicarbonate. And again, another information that came from the chemistry was that all the water that were filtered became richer in nitrate. We didn't know why. So we're trying to solve one problem, but another problem was being generated. But at the end of the day, we realized that the chemistry of all the filtered water turned out to be calcium plus magnesium nitrate. Nitrate were really rich. But to come back to our focus of defluoridation, the chart there we have, these are raw water samples that we collected from boreholes that we know the concentration of fluoride already. So there we have filter G that we didn't adapt. And you will see from this chart that the concentration of fluoride, which went in the raw water sample as high as 2.5 milligrams per liter, all of that was scavenged in the filters to less than 0.5 milligrams per liter. And among all the filters that we tested, I think filter C was the less, effective. But all of them happened to produce or dispense fluoride that was acceptable for drinking in the local context and the local communities. Another thing that caught our attention was that the result that we got from Hanover, Germany, showed that some of the samples were really rich in uranium, with concentration as high as 85 micrograms per liter. But as we're doing the defluoridation process, these prototype filters that we're targeting to remove fluoride also remove uranium. And this was really surprising to us. And we had to find out after why this happened. But before we go into that, we concentrated in considering that if we have to produce these filters for the local community, we asked ourselves a question: how long will the local population in those villages use the filters before they get saturated? Because as the water is being dispensed, the fluoride gets absorbed to the calcium and form the mineral fluoride, which is just deposited in the materials in there. So for how long can it get saturated before the local community can get somewhere to get new material to change in the filter components? So we carried out a kind of temporal observation of the filters for close to about 2 months, 3 weeks. And we realized that one of the filters, which is we characterize as filter B, stayed constant after removing the fluoride for the entire period of, of the weeks that we use. But the other filters, you had gradual increase in fluoride with time. So filter B, which had its peculiar characteristics with the content of, the charred bones and the marble that we put in there, seemed to be more reliable for the period that we did the observations. So we're able now to select which of the filter components could be more effective in this process of defluoridation. And our next challenge was to know exactly what was the component in these charred bones that we produce that is actually taking off the fluoride from the groundwater. So we collected 4 samples of the charred bones that were pyrolyzed under different temperatures in the furnace and at different durations. And we sent all of this to the lab in Hanover. And the dominant component in this material was calcium oxide and phosphate. So we concluded that calcium phosphate is the material that is absorbing the fluoride. And at the same time, the uranium and even arsenic that was identified in the water. So these are just the mechanism of the absorption. We went further to do some column experiments in Germany, and we put in different spikes of fluoride content, during the column experiment. And we realized that with the different inputs, the fluoride concentration dropped in most cases with each of these bone char to a value less than the WHO limit. But at the beginning, we're targeting the local threshold limit. But we realized that the material needed to be treated more and better for it to be more effective after the column experiment. So in all of this process, as I said, capacity building through citizen science was really conducted so that people should know in the local area what is happening, what is being done, in order to curb this situation. I want to say that the social implication of the work that we did involving citizen science made the local population to understand that fluorosis is caused by the water that they consume and not witchcraft. So the affected youth that suffered from social discrimination and stigmatization are now enjoying social cohesion in their various communities. And the affected person who felt ashamed to smile in public do so now with some confidence because they don't stigmatize them as coming from a family that is practicing witchcraft. So that was the social aspect that we thought we impacted in this area in order to give hope to the despair that many of these affected children were suffering from. Looking at the climate change angle, we realize that the quantity of water that is consumed is based on the atmospheric temperature. So in the incidence of climate change, the atmospheric temperature will keep increasing. So we had to look for an adaptive measure that is related to the norms of fluoride in water that is being consumed. So we went back into records, and we realized that in the year 1900, the atmospheric temperature was somewhere between 27 and 28. And when we put that in the equation, the norms of fluoride in drinking water should be around 0.7 milligrams per liter. As the atmospheric temperature increases, the norms is supposed to reduce. And when we project to 2080, what is expected to be the atmospheric temperature in that area at 35 degrees, so the concentration of fluoride that will be desired in drinking water should be around 0.62 milligrams per liter. So it is a dynamic process. The norms of fluoride in groundwater that is being consumed should not be a kind of stable value, but it should change with time. And this is a corner of the work that we are trying to exploit to look at one measure to adapt to the impact of climate change that we are living in. With this story, we face some challenges. The challenges of seeking for sufficient financial resources, the challenges of involving top politicians to use evidence-based knowledge to ignite effective and sustainable defluoridation process, the challenge of communication, especially on scientific platform, because sometimes it's very frustrating. I just want to share this experience. You write up a manuscript and you send to a journal, and before you turn off your computer, you are getting a message, rejected. we like hovered and hovered, and we finally got it anchored in one journal, but we think that there are some of these stories that touch the local community where the science of it is not coming out as strong as expected. But we think that the interaction between science and the local population is very vital, because we are all human beings and we live with people and we interact with people, and we have to make sure that people are living a better life with what we do. Another challenge is that of, changing science for partnership, for developmental partnership. Because I think what we need now is to do science for development more, but the environment is not enabling yet in our setup. So to conclude, we concluded that the very calcium phosphate, which was a provenance of fluoride that caused dental fluorosis, turned out to be the same material that absorbed fluoride in the bone chars. The second conclusion, which is based on the social component, is that the comprehensive hydrogeochemical data or information was successfully used to debunk and demystify the origin of dental fluorosis, thus transforming despair to hope in affected people who became accepted by the local communities, and they now enjoy social cohesion and inclusiveness. Within the context of climate change, one measure of adapting to the impact of climate change is to always reset the fluoride norms in drinking water based on increasing atmospheric temperatures. And for sustainability, capacity development of 25 stakeholders were effectively done in the community through initiating citizen science. For perspective, we look into the future to produce a comprehensive hydrogeochemical map in the area in order to guide, borehole drillers on where to drill boreholes for the supply of drinking water in that area. We want to purchase or reconstruct a more user-friendly furnace or pyrolyzer to facilitate effective charring of the raw cow bones. The duration to saturation of the defluoridation filter should be determined in order to ensure timely frequency of replacing the filter content at the home level. We have to refine engineering inputs to transform the prototype defluoridation filter into an industrial product that will also save other fluorosis-prone neighboring countries like Nigeria, Chad, and other countries in sub-Saharan Africa. We have to elucidate what is happening, that during the process of defluoridation, nitrate concentration is increasing. We don't know what is happening yet. And we have to reorganize a more effective citizen science process in the fluoride, fluorosis, defluoridation nexus in the context of climate change. So the Institute of Geological and Mining Research in Cameroon welcomes any form of collaboration and cooperation that will stop the vulnerable communities from consuming groundwater with undesirable concentration of fluoride. I wouldn't stop without acknowledging all of these organizations: UNICEF, the JICA of Japan, the University of Toyama, the BGR in Germany, Global Water Partnership, UNEP, Global Water Partnership, Central Africa, and not forgetting the Geochemical Society and the European Association of Geochemistry that has made it possible for me to disseminate this information with you here today. For all of what has been done. in this endeavor. Thank you all for your kind attention.
Thank you very much for such a fascinating and wide-ranging presentation. We have a time for maybe one or two questions, if there are any. If you have a question, please go to the microphone. Okay, we have one question coming.
It's more of a suggestion. It might be that the high temperature in your furnace is actually causing the high temperature oxidation of N2 from the atmosphere and forming the nitrate.
Thank you.
Thanks very much. Any other questions before we depart for lunch? Okay, well, let's thank Wilson again.